x is 0, 1, 2, and xi, so that means xi follows binomial 2 comma theta, and t is given as summation I is equals to 1 to n xi. So that means like t follows binomial 2n comma theta. So if we see the statements, so given first statement is saying t is a complete sufficient statistic for theta. So that means first if we consider the joint likelihood of L of theta, so that is product I is equals to 1 to n, 2 choose xi, theta to the power xi into 1 minus theta whole to the power 2 minus xi, which is nothing but the product of 2 choose xi into theta to the power summation xi into 1 minus theta 2n minus summation xi. So that means like this likelihood depends on data only through the summation xi. So t is equals to summation xi. So therefore we can say that t is sufficient. So now this t follows binomial n comma theta. So t follows binomial with parameters 2n comma theta. So the family, so this family is a full one parameter exponential family, and with fixed support, and binomial family is complete. So therefore t is complete sufficient. So hence t is complete sufficient. So therefore statement 1 is true. Now for statement 2, so t is following binomial 2n comma theta. So that means expectation of t into t minus 1 is nothing but 2n into 2n minus 1 theta square. So that means expectation of t square minus t by 2n into 2n minus 1 is nothing but theta square. So therefore it is unbiased. So now so it is unbiased. Now since the estimator, so if you see this estimator, it is a function of, this estimator is a function of the complete sufficient statistic t, complete sufficient statistic t. So therefore by Lehmann-Scheffé theorem, it is the uniformly minimum variance unbiased estimator, UMVV. So therefore both statements are correct. So option C will be the correct answer.